Hello, in this lecture we will find the area of the small circle. In the drawing we have two circles with an internal lunge between them at this point. Let's call this point N. The two circles touching each other at point N. They have internal lunge between them at point N, and also the small circle has three tangents. This is the first tangent, this tangent is tangent to the circle at this point. Let's call this point S. Also we have the first tangent. This tangent is tangent to the circle at this point. Let's call this point Z. And we have the third tangent. This tangent is tangent to the circle at this point. Let's call this point M. Point M is the point of contact between the tangent to the circle, or the touching point between the tangent to the circle and the circle. So we have 3 points of contact between the tangent to the circle and the circle, or points of tangency, or 3 points of lunge points between the circle and the tangents to the circle. And we also know that this is a right angle and this is also a right angle. So actually this also will be a right angle, because this is the straight line, and we know that the sum of the angles along a straight line is 180 degrees. So if this is a right angle, this is also must be a right angle. The same thing is here. We have here 90 degrees. So along the straight line at a certain point, we have the sum of the angles is 180 degrees. So this angle also must be a right angle. And we know that AB is the diameter of the big circle. So actually AB equals to 2 times the radius of the big circle. Let's define the radius of the big circle as capital R. So A equals to 2 times capital R. AB equals, chord AB equals to 2 times capital R. That is the radius, 2 times the radius of the big circle. And we also will define the center of the small circle as point Q, and the center of the big circle will be defined as point P. And we know that AC equals to 9 units and DB equals to 4 units. And we want to find out the radius of the small circle. Let's define the radius of the small circle as small r. Okay, r is the radius of the small circle, and capital R is the radius of the big circle. And we defined point Q as the center of the small circle, and we also defined point M as the center of the big circle. Point M is the center of the big circle, okay. So I will read the things that I wrote. R is the radius of the small circle, and capital R is the radius of the big circle. Point Q is the center of the small circle. This is point Q, the center of the small circle, and point P is the center of the big circle. That is to say, AP is capital R, and PB also equals to capital R, and AB equals to R plus R. That is to say, AB, that is the diameter of the big circle, equals to 2 times capital R. Okay. In the next step, we will draw 3 radiuses of the small circle. We will draw the radiuses to the point of tangency here. This is the radius, small r, of the small circle. We drew the radius in that way that it touches point S, it touches the point of tangency between the tangent and the circle, and we will draw the second radius from the center of the circle, point Q, that is to say point Q, to the point of tangency between the tangent to the circle and the circle itself. Okay, and we will draw the third radius in such a way that it touches the point of tangency between the circle and the tangent to the circle at point S. So R touches the circle at point Z, that is the point of tangency between the tangent to the circle, and also this radius touches the circle at the point of tangency, and this radius also touches the circle at point S, that is the point of tangency between the tangent and the circle. Okay, so actually we have a rule number 1. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. So I will read rule number 1 again. Rule number 1 states that the tangent to the circle is perpendicular to the radius at the launch point. So here S is the launch point between the circle and this tangent. M is also the launch point between the tangent to the circle, and point Z is also the launch point between the tangent and the circle. And rule number 1 states that the tangent to the circle, that is to say this line segment, is perpendicular to the radius at the launch point. The launch point is point S, and according to rule number 1, the tangent, this line segment, is perpendicular to the radius at the launch point. The radius is drawn to the launch point, and according to rule number 1, the tangent is perpendicular to the radius at the launch point. So if you draw the radius in such a way that it touches the launch point, that is to say it touches point S, then the tangent will be perpendicular to the radius. That is to say this angle is a right angle, it equals to 90 degrees. Okay? And the same thing here, we have radius that is drawn to the launch point. M is the launch point between the tangent and the circle, and the radius is drawn to the launch point. It touches the launch point, point M. For that reason, according to rule number 1, the tangent is perpendicular to this radius, because the radius is drawn to the launch point. That is to say, the radius is drawn until it touches the launch point, point M. So therefore, the tangent is perpendicular to the radius. That is to say, this angle is a right angle, and also this angle is a right angle. Okay, so whenever you draw a radius that is drawn to the launch point, then the tangent will be perpendicular to that radius. So all the radiuses here are drawn to the launch point. For that reason, the tangent is perpendicular to those radiuses. Here also the radius is drawn in such a way that it touches the launch point, so it's drawn to the launch point, that is point Z. Therefore, the tangent is perpendicular to that radius. Whenever you draw a radius that touches the launch point, that is drawn to the launch point, then the tangent will be perpendicular to that radius. So we have here three right angles. Okay? Again, according to rule number 1, whenever you draw a radius in such a way that it touches the launch point, then the tangent will be perpendicular to that radius. So this radius touches the launch point, point Z, therefore the radius is perpendicular to the tangent, or the tangent is perpendicular to the radius. It is the same. And here also the radius is drawn to the launch point, it touches the launch point, therefore the radius will be perpendicular to the tangent. And also here the radius is drawn to the launch point, or it touches the launch point, that is to say it touches point S, that is the launch point, therefore the radius is perpendicular to the tangent, or the tangent is perpendicular to the radius, it is the same. So anyway, this is the right angle. Okay, so actually here we have a quadrilateral QZMD is a quadrilateral QZMD is a quadrilateral with 3 right angles. 1, 2, and 3, those are right angles. So the sum of those 3 angles is 90 degrees times 3, 270 degrees. Okay, the sum of the 3 angles of the quadrilateral QZMD, this quadrilateral, equals to 270 degrees. And we have rule number 2 that states that the sum of the angles in a quadrilateral is equal to 360 degrees. Okay? Rule number 2 states that the sum of the angles in a quadrilateral is equal to 360 degrees. So according to rule number 2, the sum of the angles in quadrilateral QZMD equals to 360 degrees. So we have 3 angles, that the sum of those 3 angles is 270 degrees. So in order to complete the sum of the angles, of the 4 angles of this triangle to 360 degrees, the 4th angle must be equal to 360 degrees minus 270 degrees. Okay? So the value, the size of the 4th angle must be equal to 360 degrees minus 270 degrees in order that the sum of the four angles will be equal to 360 degrees according to rule number 2. So the side of the fourth angle must be equal to 90 degrees. Okay? So this is a right angle. Okay, so we have here a quadrilateral with four right angles, and according to rule number 3, rule number 3 states that if a quadrilateral had four right angles, then it is a rectangle. Okay, so I write down rule number 3. Rule number 3 states that if a quadrilateral has four right angles, then it is a rectangle. Okay, according to rule number 3, if a quadrilateral has four right angles, then it is a rectangle. So we have here quadrilateral QZMD that has four right angles. Therefore, according to rule number 3, quadrilateral QZMD is a rectangle. Okay, I write it down. Quadrilateral QZMD is a rectangle according to rule number 3. Okay, because of the fact that it has four right angles. Okay, quadrilateral QZMD is a rectangle according to rule number 3. So we know that quadrilateral QZMD is a rectangle, and we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. Okay, rule number 4 states that the opposite sides of a rectangle are equal to each other. I will read rule number 4 again. Rule number 4 states that the opposite sides of a rectangle are equal to each other. So, actually, according to rule number 4, QZ is equal to MD, and also QM equals to ZD, but we will focus on QZ, that is equal to MD. According to rule number 4, QZ, side QZ equals to side MD of the rectangle QZMD. Okay, and we know that QZ equals to the radius of the small circle, that is to say QZ equals to small r. So we can deduce from this equality that MD equals to small r. Okay, so MD equals to small r. Okay, so we proved that line segment MD equals to the radius of the small circle. We have here exactly the same situation. We have quadrilateral SQCM that has 3 right angles. Therefore, according to rule number 2, the fourth angle also must be equal to 90 degrees because of the fact that the sum of the angles in a quadrilateral equals to 360 degrees. Okay, so if the other 3 angles, the sum of them is 270 degrees, in order that the sum of the 4 angles will be equal to 360 degrees, the fourth angle also must be equal to 90 degrees. Okay, and we know that if a quadrilateral has 4 right angles, it is a rectangle according to rule number 3. And we know, according to rule number 4, that the opposite sides of a rectangle are equal to each other. So SQ equals to CM and SQ equals to small r. So CM that equals to SQ must be also equal to small r. So we proved that CM also equals to small r. And in the next step, we will define PM as x, that is to say PM equals to x, and the value of CP equals to CM minus PM. Okay, the value of CP is CM minus PM, but CM equals to x according to our definition, and we have already found out CM equals to R. That's what we have already found out, and PM equals to X according to our definition. So actually CP equals to R minus X. Again, CP equals to CM minus PM, and we have already found out that CM equals to small r and PM equals to X according to our definition. So CP equals to small r minus X. Okay, so I'll write it down here in the drawing that the value of CP is actually small r minus X. Okay, in the next step we will calculate the radius the size of the radius of the big circle in two different ways. The radius of the big circle, that is to say capital R, equals to AP from one side, but the radius, because P is the center of the circle, so the radius of the big circle equals to AP, and from the other side the radius of the big circle also equals to PB. Okay, so we create two equations that they are actually the expressions of the radius of the big circle in two different ways. Okay, so the first equation is actually states that the radius of the big circle is capital R equals to AP. Capital R, the radius of the big circle, equals to AP. But what is the value of AP? AP equals to AC plus CP. Okay, AP equals to AC plus CP. Okay, the radius of the big circle equals to AP, but AP equals to AC plus CP. And we know that AC equals to 9 units. It is given us in the question. Okay, plus CP, we have already found out that the value of CP is R minus X. So in total we got that the radius of the big circle capital R equals to 9 plus R minus X. So I write it again, that the radius of the big circle equals to 9 plus R minus X. Okay, that is the first way to calculate the radius of the big circle, but the second way to calculate the size of the radius of the big circle is actually to say that the radius of the big circle equals to PB. Okay, P is the center of the big circle, so PB is the radius of the big circle. That is the second way to calculate the radius of the big circle. Okay, so we will write down that the radius of the big circle equals to PB. Okay, but what is the value of PB? PB equals to BD plus MD plus PM, or PB equals to PM plus MD plus BD. Again, PB equals to PM plus MD plus DB. Okay, PB equals to PM plus MD plus BD. Okay, so actually the radius of the big circle equals to PM. What is the value of PM? According to our definition, PM equals to X. And what is the value of MD? MD equals to R, according to what we found out, according to the rules that I gave you. MD equals to small r, and BD equals to 4. It is given us 4 units. It is given us in the question. So in total we got the value of the radius of the big circle according to equation number 2. The radius of the big circle equals to X plus R plus 4. So we have two expressions of the radius of the big circle. Okay, because it is the same circle with two different expressions. Of course, expression number 1 in equation number 1 will be equal to expression number 2, that is actually the expression of the same circle. So we will compare equation number 1 to equation number 2, and we will get that equation number 3 that states that the radius of the circle according to equation number 1 is 9 plus small r minus x, and according to expression number 2 and equation number 2, the radius of the big circle equals to x plus small r plus 4. Okay, we add two expressions of the radius of the circle. Expression number 1 equals to expression number 2 because we are talking of the same radius. So we got this expression here. We have r in this side of the equation and we have r on the other side of the equation, so we can cancel r. So what is left after we cancelled r is 9 minus x equals to x plus 4. Okay, here we will subtract 4 from this equation and we will get 9 minus 4 is 5. 5 minus x equals to x. Here we will add x to this equation and we will get that 5 equals to 2x. We will divide this equality by 3 in order to get the value of x. So x will be equal to 5 over 2. 5 over 2 is 2.5 units. So we found out the value of x. X equals to 2.5 units. Okay, x equals to 2.5 units. And we have equation number 1 that expresses the radius of the big circle according to expression number 1. The radius of the big circle is equals to 9 plus small r minus x. But we have already found out that x equals to 2.5 units, so we can substitute x in equation number 1 by 2.5 units. And we will get that capital R, the radius of the big circle, equals to 9 plus small r minus 2.5. Okay, so capital R equals to 9 minus 2.5 is 6.5 plus small r. So actually we found out that the radius of the big circle equals to 6.5 plus small r, and x equals to 2.5 units. In the next step, I will present rule number 5, and we will use rule number 5 in our drawing. Okay, rule number 5 states that if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So I will read rule number 5 again. Rule number 5 states that if two circles have internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so if two circles touch each other internally, then at one point, then according to rule number 5, the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so the distance d equals to r1 minus r2 if r1 and r2 is the radiuses of the circles. Okay, d equals to r1 minus r2 when d is the distance between the centers and r1 and r2 are the radiuses of the two circles. Okay, so actually we can implement rule number 5 in our circles because we have here two circles with an internal lunge at point N. The two circles are touching each other at point N internally. Okay, so we can implement rule number 5 in this drawing. According to rule number 5, the distance between their centers, we know that the center of the small circle is at point Q and the center of the big circle is at point P. So the distance between the centers is QP. So QP equals to, according to rule number 5, QP equals to the difference between the lengths of their radiuses. The radius of the big circle is capital R and the radius of the small circle is small r. So we can write down that according to rule number 5, that will be a question number 4, QP, that is the distance between the centers of the two circles, will be equal to capital R minus small r. Equation number 4 is the implementation of rule number 5 on our two circles. Because QP is the distance between the centers of the two circles, and the distance between the centers of the two circles according to rule number 5 is equal to the difference between the lengths of the radiuses, and the difference between the lengths of the radiuses is capital R minus small r. So QP, that is the distance between the centers of the circles, equals to capital R minus small r. Okay, here we will add small r to this equation, and we will get that capital R equals to QP plus small r. Okay, so we got the expression for the radius of the big circle, and we have the expression of the radius of the big circle according to equation number 1. We know that capital R equals to 6.5 plus small r. Okay, so we have the expression of the radius of the big circle in two different equations. So because it is the same circle, we can compare equation number 1 to equation number 4. R equals to R. Okay, and it will be equation number 5. It states that QP plus R, that is the radius of the big circle, equals to 6.5 plus small r, that is also the radius of the big circle. Okay, so here we have small r on this side of the equation, and we have small r on this side of the equation, so we can cancel r, and we actually got the value of QP from equation number 5. We know that QP equals to 6.5 units. Okay, and we have also found out that X equals to 2.5 units from equation number 3. So here we will connect together points Q and P by a straight line. Actually, triangle QMP is a right triangle because this angle is a right angle. In the right triangle QMP, we know that QP, the hypotenuse of this right triangle, equals to 6.5 units. We know that PM, that equals to X, equals to 2.5 units. And the only missing variable is QM, that is the radius of the small circle that we want to find out. So we can use the Pythagorean theorem in order to find out the value of the radius of the small circle. Okay, so according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to PM square plus QM square. That is actually according to the Pythagorean theorem. Okay, according to the Pythagorean theorem, QP square equals to PM square plus QM square. But we have already found out that QP equals to 6.5 units. So QP square is 6.5 square. And PM equals to X. And we have already found out that X equals to 2.5 units. So PM square is 2.5 square. And QM equals to small r is the radius of the small circle that we want to find out. So actually we have here only one missing variable. Okay, we got the equality that 6.5 units, 6.5 square equals to 2.5 square plus small r square. 6.5 square is 42.25 and 2.5 is 6.25. So I will write it down. So we got the equality that states that 42.25 equals to 6.25 plus r square, small r square. We will subtract 6.25 from this equality and we will get that r square equals to 42.25 minus 6.25 equals to 36. So here we will take a root out of this equality and we will get the value of small r, that is the radius of the small circle. So we'll get that the radius of the small circle equals to 6 units. Okay, so we found out that the radius of this small circle equals to 6 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the radius of the small circle. We know that the two circles are touching each other at point N. They have internal lunge between them at point N, and we know that the small circle has 3 tangents. This tangent is tangent to the circle at point S. This tangent is tangent to the circle at point M, and this tangent is tangent to the circle at point Z. So we draw 3 radiuses to the points of tangency between the circle and their tangents. Okay? This radius starts from the center of the circle and ends at point S. Actually, it touches point S. So we have here 3 radiuses that are drawn to the points of tangency between the circle and between them. So according to rule number 1, one states that the tangent to the circle is perpendicular to the radius at the launch point. Actually, the radius touches point S. Okay, the radius is drawn to the launch point. Therefore, according to rule number 1, the radius is perpendicular to the tangent. This is a right angle. For the same result, this is also a right angle, and this is also a right angle, because the radiuses are drawn to their points of tangency. For that reason, the angle between them to the tangents is a right angle. Okay? So for that reason, this is a right angle, those two angles are right angles, and this is also a right angle. And we know that this is a right angle and this is a right angle also. So we have QZMD is a quadrilateral QZMD is a quadrilateral with three right angles, and we have rule number 2 that states that the sum of the angles in a quadrilateral equals to 360 degrees. So the sum of the three angles, the three right angles, is 270 degrees. And in order that the four angles will be equal to 360 degrees, the fourth angle must be also equal to 90 degrees. So the size of the fourth angle is 90 degrees. So we have here a quadrilateral with four right angles. And according to rule number 3, if a quadrilateral has four right angles, it is a rectangle. So quadrilateral QZMD has four right angles, therefore according to rule number 3, it is a rectangle. And we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. So we know that QZMD is a rectangle and the opposite sides are equal to each other. That is to say, QZ equals to MD. QZ equals to MD, and QZ also equals to the radius of the small circle, and QZ equals to MD. So MD must be also equal to the radius of the circle. And we also repeated on the same process on quadrilateral SQCM. It has three right angles, so the fourth angle must be equal to 90 degrees according to rule number 2. And because of the fact that it has three right angles, according to rule number 3, it is a rectangle. And according to rule number 4, the opposite sides of the rectangle are equal to each other. That is to say, SQ equals to CM. But SQ equals to small r, so SQ that equals to CM, or CM that equals to SQ, must be also equal to small r. Okay, so CM equals to small r. Okay, then we define PM as X, we know that Cm equals to small r, so Cp equals to Cm minus Pm, that is to say Cp equals to small r minus x. Okay, so the radius of the big circle equals to AM, and AM equals to AC. The radius of the big circle equals to AP, and AP equals to AC plus CP, but AC equals to 9 units and CP equals to R minus X. So actually the radius of the big circle, according to equation number 1, must be equal to 9 plus R minus X. Okay, and we have the radius. We created second expression for the radius of the big circle. The radius of the big circle also equals to PB, because P is the center of the circle. PB is the radius of the big circle. But what is the value of PB? Actually, PB equals to PM plus MD plus DB. Okay, so actually R that equals to PB equals to X, PM equals to X, MD equals to small r, and BD equals to 4. So actually the radius of the big circle, according to expression number 2 and the equation number 2, equals to X plus small r plus 4. So we have two expressions of the same radius. Therefore those two expressions are equal to each other. So we compare the equation number 1 to equation number 2, and we created equation number 3, and from equation number 3 we got the value of x. We found out that x equals to 2.5 units. So the radius of the big circle, according to equation number 1, equals to r plus the radius of the big circle, capital R, equals to 9 plus small r minus x. We have already found out the value of x. X equals to 2.5 units, so we can substitute x by 2.5 units. So we got that the radius of the big circle equals to 6.5 plus small r. And we found out that x equals to 2.5 units. Then we presented rule number 5, and we implemented rule number 5 in our two circles. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So if two circles touch each other internally, then the distance between their centers equals to the difference between their radiuses. Okay, so if this is the distance between the centers of the circles, and R1 and R2 are the radiuses of the two circles, then D equals to R1 minus R2 according to rule number 5. So we implemented rule number 5 in our circle, because in our circle we have an internal length between those two circles at point N. Therefore we can implement rule number 5 that states that in this situation the distance between the centers of the circles, that is to say QP, equals to the difference between their radiuses. QP equals to capital R minus small r. Okay, so we know that QP equals to capital R minus small r, and we have already found out that capital R equals to 6.5 plus small r. So because it is the expression of the same radius, we can compare those two expressions. Equation number 4 equals to equation number 1. So we created in this way equation number 5, and we found out that QP equals to 6.5 units and X equals to 2.5 units. Then we connected together points Q and P and created the red right triangle. It is a right triangle because of the fact that angle Q and P equals to 90 degrees. So in this right triangle we implemented the Pythagorean theorem in order to find out the value of QM. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square equals to PM square plus MD square, and we know that QP equals to 6.5 units and PM equals to 2.5 units, and the only missing variable is the radius of the small circle. We solved this simple equation and we found out that the radius of the small circle equals to 6 units. Again, the radius of this small circle equals to 6 units. Okay, thank you very much.